us Dr. Breno Fregomeni. Dr. Fregomeni has been an assistant professor at the University of Connecticut since 2018. He is specialized in genomic prediction with a focus on the prediction of complex traits related to heat stress tolerance, welfare, disease resistance, behavior, and production. In addition, his research focuses on investigating genomic aspects underlying such complex traits, with the overreaching goal of improving the quality of genome-wide association studies, or at least understanding its limitations. His lab has experience with several species, including dairy and beef cattle, shrimp, rainbow trout, swine, and dogs, among others. And when he's not teaching, running BLUP, or writing board transcripts, he likes to spend his time with his daughters. So thank you for joining us, Dr. Fregomeni, and I'll give the floor over to you.
Thank you for the introduction, and thank you all for the invitation. It is a great pleasure to give this talk here. So today I'll be talking about implementing genomic selection programs for heat stress tolerance in livestock. The way I'm going to approach it, I'm going to talk a little bit about GBI. I'm going to talk about some of the statistical methods that we can use to investigate GBI, some of the limitations, some of the advantages. When you go for genomic data, I'm going to just do a quick comparison between multi-step and single-step approaches. And then I'm going to start sharing some examples. I'm actually going to use some of the results from previous studies in pigs and dairy to illustrate the methods, mostly the big ones, because that's concluded. So it's easier to show what worked and what didn't. But then I'm going to tell the story, what we did for the pigs, what we are doing now for dairy cattle. And then I'm going to go back and just illustrate some other challenges. And then I'm going to bring back some experience from other species as well. So on Wednesday, I actually gave a talk in Russia, also virtual. So I didn't have to go anywhere. I just had to wake up very early. And they asked me to talk about international genetic evaluations. And basically, they wanted to use genetic evaluations from other countries. Actually, they wanted to understand what would be the impact of using genetic evaluation for other countries. And it was very funny for me because I have in my backyard. So the picture on the left-hand side is my backyard. Let me see if I can. Yeah, I don't have, oh, pointer here. So yeah, so that's this tree here in my backyard. It was actually brought from the previous owner of my house from Russia. And that's how the tree is supposed to look like. I don't know if it's just bad management, but the tree is not well adapted to our environment. And I was trying to illustrate showing that if we don't have a good match of genetics and environment, we're not going to see what we're expecting to see. I don't know how much Photoshop's on the right-hand side, but it looks much better than mine. What is our goal? So why do they pay me for? To tell which animal is the best one. Now, animals are different from each other for several reasons. They are exposed to different environments and they have different genetics. If we can identify the genetics that makes one animal better than the other, and we let those animals breed, well, we're going to improve domestic species. The whole goal of what we do is to differentiate what is genetic and what is environmental. And once we do that, we can basically breed the animals with better genetics. We know how complicated it is to separate genetics from the environment. And then we have an extra problem that it's actually a little bit more common than we think. That is, prediction models sometimes will fail. Sometimes we do everything right. We calculate breeding values. We think we have a high accuracy, but we do not see a selection to response as good as expected. Or we see a big re-ranking after collecting data. of the animals, and there are many reasons for that. Today we're going to focus on one of them, that is genotype by environmental interaction. And basically, the most simple definition of that is when different individuals will respond differently to multiple environments. So the best animal for a given environment, it's not necessarily the best one for another one. So if we select the animals based on one specific environment and we evaluate the progeny in a different one, we may lose accuracy and our models then will fail. That is a big problem because sometimes we cannot tell what is the environmental value. I have that slide here that was from a different talk as well. Probably I'm just stating the obvious for most of you, but every time we talk about genotype by environmental interaction, we must think that we're actually dealing with two different traits or more than two different traits, because the phenotype that is measured in a given environment is not necessarily the same as the phenotype measured in the other one. If they are the same, then we go to the case if we have a positive and high genetic correlation, meaning that both genetic merits are gonna work. But the more different the environments are, well, the genetic correlation decreases, and then selecting for one trait is not necessarily going to promote the same improvements for other environments, for breeding values for the other environment. The rule of thumb that we use is genetic correlations less than 0.8 may suggest that we're now dealing with two different traits. And why 0.8? Well, why not 0.81? I don't know. There are some papers showing that values less than 0.8 may still be analyzed together, and in some cases, values higher than 0.8 may need to be separated. So, but it's just one number for us to start thinking about it. Usually, when you're talking about G by E, we're not really thinking about really small or even negative genetic correlations. That will depend a lot on what is the environments that are comparing, what are the phenotypes, and we actually can still make progress. So this formula here is the response to selection for correlated traits. If that genetic correlation here is high, we can still make progress as we select for trait Y based on trait X. But that will be the same thing as performing a genetic evaluation with low accuracy. Is that a big problem? Well, it will become a big problem, a bigger problem every day, because we're increasing the quality of our agricultural systems. We're increasing precision agriculture applications, and we must operate with maximum efficiency. And as geneticists, how we can help them is to provide evaluations with maximum accuracy. The more we increase intensity of agriculture, the higher our accuracy must be in order to be efficient. Now, things get more complicated because we are changing focus a lot on genetic evaluations, not only for production traits, but we're talking about feed efficiency, methane emissions, reproduction, health, and so many other traits that are much more sensitive to heat stress than, let's say, milk production for dairy cattle. Over here, I have this slide that I actually took from a student of mine. And I just highlighted traits with genetic correlation below 0.8-ish. And you see that fertility, somatic cell count, fertility again, residual feed intake, all of those traits, they were on the lower end of the correlations, while production, milk, fat, protein, and some others had a little bit higher genetic correlation. So it's not always exactly like that, but we see a trend that some traits they tend to be evaluated differently when the environment changes. And basically what people are doing here, they were just comparing different countries, different production systems and so forth. How do we deal with that? Well, we need to model production losses as a function of the weather. That's the easiest way, because if you think about it, there is no phenotype that's easy to scale that is a good prediction of heat stress tolerance. For instance, there is nothing that I can go right now to the farm and measure to see, okay, this cow is actually heat stressed. People have been trying to use respiration rate, vaginal temperature, skin surface temperature. They try many things, and I'm going to talk a little bit about it. Most of those things are either very hard to measure in large scale, or not as efficient predictors of heat stress. So running an evaluation for that is going to become extremely complicated. What we know is that, and that's an example here in pigs, is that as we increase thermal discomfort, the performance of those animals decrease. So we see here, for example, a weight loss of the animals associated with the temperature that they were slaughtered. Can we take advantage of that? Can we find what is actually causing those animals to lose weight on the genetic side, and then select for animals that will lose less weight? We definitely can. The very first thing will be defining what is going to be our environmental gradient here. So usually for heat stress, we use the THI, which is a temperature humidity index. We're going to talk a little bit about it. Or what we call a heat load function, which is the number of degrees exceeding a certain threshold. Why is that important? If we just feed temperature alone or THI alone, we may find artifacts saying that the colder it is, the better the animal is going to perform. And that's very dangerous. Sometimes modeling for just the THI or the heat load, we cannot find a lot of response to heat stress. But when you look at overnight cooling, that makes a huge difference. It depends on the system, depending on the farm. When animals are not able to cool overnight, then on the next day, they will show symptoms of heat stress much more than if they're exposed to much higher temperatures, but they have the chance to cool overnight. And there are actually many other metrics. We usually stay in THI and heat load just because that's what we have most papers about. And they actually yield pretty good results for dairy cattle and for pigs. But there are many other things that we can do. What we have to do now, we have this regression here aligned, right? We have this regression here. We have the linear and the quadratic regression. We have the observed phenotype. Now, if we can model that with a random effect of animal, we should be able to detect that. What we have to do, we have to nest those regression coefficients into animal and use the various covariance structure as we use in a regular animal model. And basically, when we do that, we will be able to model those losses. Or basically, we can find a threshold here and decide when it's cold, when it's not cold, when the animals are heat stressed, when the animals are not heat stressed. you name it, and then we consider them two different traits. And then we run evaluation for trait 1 and 2 together. We calculate genetic correlations, and we have breeding values for both environments. In multi-trait evaluations, each one of our phenotypes is assigned to a group. I like to call them hot and cold just to make it easier. Usually when we write the papers, we come with better names. And we just run a 2-trait, or depending on what you want to do, twice more traits than we were running, given that every trait was collected in a different environment. And then we calculate genetic correlations. Those genetic correlations, changes in heritability, change in sire ranking, that will allow us to identify the extent of heat stress in that population. Inside the genetic part of it, right? This type of model is very easy to identify. We have all the machinery already. We just have to split that into 2 traits. The first problem is deciding the threshold that will separate the analysis. So how would we find a threshold? That's I'm going to answer in the next slide. And the problem is, what if the animal is very close to that threshold? Should we throw away that data, or should we assume that this animal belongs to one group or the other? That becomes very complicated. The other thing is, when I have an animal that is slightly heat stressed and an animal that is under extreme heat stress, if we only have 2 groups, they're going to be grouped together. Usually from the comfort group, that's not a big deal. But for the heat stress group, we may have different levels of heat stress. Some people may suggest that we have to do more than 1 group for heat stress, but then increasing the number of traits has a cost computationally and statistical as well. So you got to be careful on coming with more and more and more new traits. How do we calculate that threshold? Well, first thing that we do, we calculate the THI, which is the temperature humidity index. It's not the only way we can do it. It's probably the most common one. Based on what I have in the literature, I would say it's the most common one. We calculate that heat stress, and then we have to calculate what we call a heat load function, which is the maximum between 0 and the difference between our THI for that observation and a threshold. The problem is, what is that threshold? So what I want to know is, when are the animals actually being heat stressed? What I did for that thing here, so in the right-hand side here, that was we're testing different THI thresholds for the pigs, starting at 55 THI, all the way to 80 THI. And each one of the colors here means a different period under heat stress. So the 70 days here represents 70 days. The THI averaged above each one of those thresholds for 70 days, for 60, 50, 40, and 30 days. And I just plotted the R squared for those equations, and I picked the highest one. That was around 74 to 75 degrees. I'm sorry, 74 to 75 THI. One could say that 72 was also high, but they're very similar values, actually. And that was a threshold. Everything above that value here could be considered a heat stress record. Everything below that was actually a non-heat stress value. What we did, we used those thresholds here to split our data in 2. We used the same model as a single trait analysis. And the only thing we have to do is to assume a variance covariance structure between heat stress and non-heat stress. And we use those covariances to estimate the values. Most of the times we cannot calculate environmental covariance because we only have records for each animal in each one of the groups. And the common environment here, in this case, was the litter effect for swine, we could also not calculate that because every animal in a common environment was always collected only for a single trait. In some cases, when you can collect animals for more than one trait, we may be able to calculate those residuals or common environmental effects. What we can also do is that we can account for each degree in heat load or THI, treating them as longitudinal values. So instead of dividing them into heat stress and non-heat stress, we can just assume that they are longitudinal values. That makes our life much easier because we don't have to establish thresholds. Sometimes we have to come up with a threshold just for the heat load. Otherwise, we start overfeeding, especially on the cold part of it. So the colder it gets, depending on how it goes, we may say the animal gets better. So we still have to do a heat load, but it's not as critical as the threshold for the two-trait analysis. It sounds like a great idea, modeling those losses to be something much more similar from what we observe here. We see that linear decrease in phenotype, so we just use that as an assumption. But you gotta be careful because there is a huge risk of overfitting, so you gotta be very careful as we add complexity to those random regressions. In addition to that, calculating variance components and doing validation may become extremely complicated, especially when we have a lot of data. Sometimes it's not going to converge, it's going to take forever, you're going to have some problems. I've been very successful using the R method and the LR method. The R method, basically, we divide our data into small samples. We calculate variance components, and we do that several times. Each one of those small subsets runs much faster, runs much smoother, and then we just combine the statistics of several runs, and we got pretty good results without going through the problem of burdening our machines with those huge data sets. And for the validation, we use the LR method, which I'm going to talk about later. So I'm going to skip that for now because I'll have the example that what we did in pigs for that. The random regression models, they will look a little bit more complicated than the single, the multiple trait model. We usually have the same fixed effects that we had. For example, here we had sex, age. The contemporary group is a little bit different because now we have a fixed curve for each contemporary group. So that's where the breeding values are going to deviate from. And the random effects, the leader, the additive, and the residual and the additive genetic effect, they may be modeled in function of the environment. In this case here, we just have one residual, one leader, but the additive genetic effect also is in function of the heat load. So we have the intercept and the slope in function of the heat load nested in each animal, same thing in each contemporary group. We can run those analyses using the same software that we use for everything. I'm a little bit biased to talk about software, but I run everything using ARM-F90 and BLUP-F90. Right now, it's just one software called BLUP-F90 Plus, and they can handle those type of analysis without any issue. Now, when you think about including genomic information, single-step GBLUP makes that a trivial implementation. So basically, what we do, we add the marker information for the animals that are genotyped, and you just run the same analysis. Probably you may need minor adjustments. The only thing that's going to happen is that random regression analysis, they tend to be heavy. If you add genomics, they become a little bit heavier. But if you have a good server, that's not a problem. If you're working on a small server, then there will be alternatives for that too. The software is becoming more efficient. The methodology is becoming more efficient, so we depend less and less and less on their server. However, data is becoming bigger and bigger. So, but you see, none of that is actually a theoretical problem. So those are only technicalities. The main problem realizes that when we do not use single-step GBLUP, what should we do? Well, calculating pseudo-phenotypes for those traits become extremely complicated. One could do that, or they could do a dairy-like approach. That's actually, I think it's still what they're doing in Australia. So what do? They define the lactation curve, right? The milk yield on a given day to build that is, I mean, there are many formulas for lactation curve. I just got the one that's the most common one. Or if you don't want to go for a lactation curve, you can just make it what we did here in our dairy. We created this model that we had a classified effect of lactation, a classified effect of lactation stage. So we have many of those kind of built in lactation curve, the heat load, and the factor for heat stress based on that. And we tested this model in several different ways. That's how we were able to model heat stress in a small farm. Very, very, very simple. The other way is to use the yield as to calculate the expected yield for each day based on the lactation curve. And then what we do, we feed the residuals of those. Of course, if we do that, the first one I have to remove the heat load, but we try to remove the lactation effect, the lactation stage, the herdier season, all the fixed effects, just to have the residuals for each test day. Then we feed the residual of each test day as a function of the heat load for each one of those values. And that slope that each animal is going to have is going to be the pseudo-phenotype. And then that pseudo-phenotype is going to be introduced in what we already call a multi-step method. So that's a multi-step method. Does that work? It does work. It's just a lot of adjustments that have to be made. It works pretty well. Our first example here that I'm going to bring was the example of heat stress in pigs. So I received this data from the swine company that I was working with. I just made a plot. I colored the bar graphs, so I plotted by month, and I colored them with intensity based on like a heat map. And what we saw was that over the summer, we had a 20-pound difference in weight. And that is a lot of losses if you think about the size of those companies. So I was going to the smaller packing plant, and over there they had about 10,000 animals being slaughtered every day. Briefly, I plotted the THI of the farms that we had data, and we saw that we had consistently every year temperatures going above what will be considered 75 THI. So there is potential of heat stress happening here. We had carcass weight of about 500,000 animals, actually, sorry, 200,000 animals on a 500,000 animals relationship matrix. We had genotypes only on the purebred sires of the commercial animals. And basically what we did, we fit the same model or very similar model that's used for their evaluation with contemporary group, sex, litter, age as a covariate, additive genetic effect, and a residual. But we fit that as a two-trait analysis in which records collected below 78 were considered comfort, and above 78 were considered heat stress. So when I showed the value before, the threshold was 75. So why did I use 78? What we saw was that 75, 76, and 77, the animals were not that heat stressed anymore. So when we consider them comfort, the model fit much better than when we consider them heat stress. Probably because those animals were much closer to the regular performance than from when animals were actually heat stressed. So that was the one. So on top of deciding the threshold using the R-squareds, we also had to test those thresholds and look at the model with the best fit. In addition to that, we use those heat loads, as I showed before, as a intercept and slope within nested in each animal. In that case here, we could use the threshold of 75 because the THI of 75, 76, 77 are now considered different values. So that was actually much better for us to do. Again, we use the regular software, ARMOF90 and BLUPF90 for everything. We did one more thing, that is we calculated genetic correlations, not only between heat stressed and comfort, but we also calculated across different states. And we saw that when we compare different states, we saw a genetic correlation that was actually much lower than one would expect, which was pretty scary. But we also saw clear effects of heat stress going on here. We didn't move too much towards this low genetic correlation between the states because that was a completely different problem, but that's definitely something I still want to go back and study one day. The genetic correlation, so what I have here is a heat map of the genetic correlations between each heat load. So on the diagonal here, we have the correlation of 1, and we see as we defer each heat load, the genetic correlation decreases. When you use different states, that becomes very scary because the genetic correlations, they already start in already 0.4, 0.5. And when we look at the way heat stress affects those animals, the genetic correlation can be almost 0, meaning that we are now performing random selection when you're doing, or no selection, when we are comparing different states and heat stress together. So those results were actually pretty scary for us when we saw that. We were expecting the genetic correlation to be much higher than that. One of the main challenges on that study was to perform the validation. We didn't have a true breeding value measurement here. We tried to use DYDs, or actually what we call progeny yield deviation here, but for a random regression model that was extremely complicated. So what we did, we used the EBV calculated with complete data as the benchmark, and then we calculated the correlation between breeding values calculated with reduced data and complete data for animals that didn't have progeny in the complete data. So we are kind of simulating the selection of young animals, and those results were actually pretty good. There was still an overestimation of accuracies under higher heat loads because we have very, very little data here. And our true breeding value had a very low accuracy. However, that is not a big concern because heat loads above 10 were not very common. They were less than 2%, I think, of our data. So we are concerned mostly about those values here. That comprised 90% or so of our data. The other thing was that for pigs, the purebred animals did not experience heat stress, which was a big surprise because we thought, well, that's those are animals that are the most advanced genetics, therefore they should be more sensitive to heat. However, their farms are much better. They had much more space. They could dissipate that heat. So we just did not experience that. So because we didn't have genotypes on the crossbreds at the time, we had to run that evaluation on the crossbred animals using genotypes of the sire. But under the animal model, that was okay, especially because we had many progeny from all the genotyped animals. So that was not a big problem. And that correlation between the EBV calculated with complete data and reduced data, that's what I call the LR method. There is a paper from Andres Legara and Tony Reverter that described that in details. If you never saw this paper, I highly recommend you to read it because you learn a lot about validation. In dairy cattle, the problem is very similar to the one in pigs. It gets hot, production decreases. Now in pigs, we have some advantages. That is, the heat stress effect accumulates over time. So remember, I was talking about the heat load calculated over 30, 40, 50, 60, and 70 days. Well, in dairy cattle, the heat stress period is much shorter. It's like a day or two most of the times. On top of that, lactation curves makes everything much, much harder because the same animal, it's going to be good because the same animal, we can have records under heat stress and under comfort. But with the lactation curves, we cannot compare those records right away. So correcting for lactation, it's extremely important. In there, it's great because we have a lot of data, but it's also awful because we have a lot of data and things just become extremely slow. The lactation curves would not be a problem if we didn't have an interaction within heat stress. So that's data collected in our dairy farming here. And here is the number of cows inseminated. And you see what happened in the summer? We do not inseminate cows that much. We start inseminating them again in October. This number in November is small because we just use one collection from the robot. So we didn't have the whole 12-month period here. But what I want to show is that as we get in October, we go back to inseminating the cows again. Same thing here, do not look at the slope. Basically, what you're saying here is the animals are not getting we're not having negative pregnancy over, but we just have less animals. I think I'm making a huge confusion here. Animals are not getting heat over the summer. Once they're getting heat, then they're not less fertile, but they're just not cycling. That leads to a huge problem because most of our animals are actually inseminated in October or November, meaning that they are going to deliver in June, July, maybe August. And then at their peak of their lactation, they're going to be under heat stress. So that thing is going to accumulate, and that makes it very, very complicated because if you don't correct for those things, you're going to think that at higher temperatures, the animals are actually doing better because they are at the peak of their lactation when heat stress is hitting the harder. So we usually expect that in dairy farms, you're going to have animals being delivered equally, uniformly over the year. But when heat stress plays a role, well, we're going to have some births being accumulated in certain periods. So you got to be careful with that. Using that information, we try to implement that into the national data in the US. First thing you're going to do is we're going to split each one of our test days into heat stress and thermoneutral. We're also going to try a random regression reaction norm. Again, we got to correct things for lactation stage, lactation, herdier season, and so forth. We try to do in different ways. We try to use just including that into our model as lactation stage, for example. We also try to correct using lactation curve and fit the residuals. We didn't find any differences, so we're not going to do this extra step for correcting the lactation values. One thing that we could do was get the lactation curve, get different parameters for each animal, and fit that as a heat tolerance component. But the preliminary results are actually quite bad, so I don't think we're going to move forward with that. Now, for dairy cattle, we have another big problem, that is farms change a lot across the country. What's going to happen, for example, if I have a record collected in Wisconsin and a record collected in Texas? Our cow that was heat stress in Texas is probably going to be cold because I have many more days under heat stress in Texas than in Wisconsin. Therefore, at least on the female side, the genetics there will be some selection against heat stress already. While in Wisconsin, because of the hot period is much shorter, I may have more heat sensitive animals. We're going to test for that. In addition of that, we're calculating if the best bull is the same across different regions. Between New England and California, we didn't find a lot of differences. There was some re-ranking. Some of the best bulls in New England were not among the best bulls in California and vice versa. But that was not a big thing that should make us split the national evaluation into more than one. Fat and protein result in slightly smaller genetic correlations. And now we are wondering what's going to happen with reproduction and health. Those are the next steps of that study. I'm going to skip that one. That was basically, we were using heat stress to model. We're using our VMS machine to model heat stress in dairy. And we found that not all animals are heat stressed the same. We have very good data. We have all the animals being milked. We have all of their records. We have, if you see this box here, that's a new weather station that we're going to install in our farm. So we're going to have even better accuracy in our data. But we saw that first lactation animals, high producing animals, and animals in the early stages of the lactation were severely affected by heat stress. And also that reproduction was severely affected by heat stress. For diseases, we found trends, but we don't have a lot of animals, so the number of cases was actually very small. But we definitely could see that mastitis and some metabolic diseases happen more often over the summer than the rest of the year. But it was very hard to model that in function of heat stress when you only had 60 animals in milk for in the hosting population. Right now, what we're going to do, we are actually working with the CDCB and AGIL to work on the national data. We're going to do a very simple model trying to do a US national heat stress evaluation. And then we're going to spend more time doing Texas and Wisconsin, just trying to see if we should be using a 2-trait model, a 3-trait model, or a random regression model. That's what we're going to do now for the heat stress in dairy. We have many challenges, though. One is that, for example, when you run GWAS in a 2-trait analysis, I may have different Manhattan plots for the trait under heat stress and not, and regular comfort. What does that mean? Does that mean that we have different genetic mechanisms acting on those traits? Maybe yes, but if I get the same trait and I split that randomly into two when I calculate a Manhattan plot, I may also find different peaks. So it's very hard to tell if those differences here are because of different mechanisms or just random fluctuations that happen in Manhattan plot. Similarly, if I try to do a GWAS for a random regression, I will have a Manhattan plot on the slope, on the intercept, or even more Manhattan plots, depending on my random regression. Those are very hard to interpret. What you can do to make it easier, we can calculate EBVs in each specific heat load of interest, and then we backsolve those EBVs to SNP effects. But then we go back to our previous issue, that is finding difference in those Manhattan plots, what they actually mean. Finally, data accessibility, it's usually not a big deal in pigs and chicken, right? But that's another challenge. So if you want to work with heat stress in pigs and chicken, you just need to find industry partners that are collecting that data, and then you can model it. In beef cattle, it's a little bit more complicated because people do not collect data as we want to model because of mating season. So most of the animals are going to be born about the same time of the year. We have a huge confounding effect between the environment and the management groups. And also, we do not collect phenotypes as often as we want to model the effect of heat stress. We did a study in cold stress, and we just had one weighting every winter, so we couldn't model much. We could tell that some years were colder than others, but we couldn't tell if the animals are actually lighter because of the year or because of the weather. It's impossible to tell. In dairy cattle, it's much easier because the animals are born throughout the year, which makes it much better. We have many records. We have very good pedigree. But accessing dairy data, at least in the US, is extremely complicated. Nobody knows who wants the data. We need to go through many agreements. But yeah, we're getting there. So very soon, we're finally going to have full access to the data, and we'll be able to do a better study. In conclusion, selection for heat stress tolerance is feasible in most livestock populations. That depends on efficient data collection and on proper statistical methods. Depending on the species, you're going to have different problems. Some of them are more administrative. Some of them are going to be more technical. That will depend a lot. The heat stress tends to become a bigger and bigger topic due to concerns with climate changes. Some breeds, they want to increase exporting to subtropical regions. And also just the regular selection that we do already decreases heat stress tolerance because they tend to be negative correlated. Therefore, people are going to be looking more and more and more to fix those problems. We need to study more statistics and more biology to fix those problems. And with that, I'm happy to take any questions. I think I went a little bit over the time. I apologize for that.
Great, thank you, Dr. Fregomeni. We'll now open the floor for questions. So if anyone has any questions or comments or discussion, feel free to raise your hands and turn on your microphones.
There is a question in the, oh, sorry.
Oh, yeah, we can start. You can also enter your question into the chat, so we can start there. So as you mentioned, purebred animals do not experience heat stress, and this is a result of their rearing conditions. So should they not be compared to crossbred pigs in the same environmental conditions so that we can see if they really do not experience heat stress, or should we compare crossbreds in the same conditions as pigs on purebred farms?
That would be the ideal case. Ideally, we would be comparing the animals in the same environment. However, we're never going to be convincing a company to, that's going to cost a lot of money. So basically, we cannot compare them. So we couldn't model losses related to heat stress in the purebred farms. But probably if they were packed in a production farm, they would suffer even more than the crossbreds. But I don't think the companies are ever going to pack their elite animals in a commercial farm, and I don't think they're going to let the commercial animals spread in a very comfortable farm because of costs, basically. But if we had the chance, that would be great.
Okay, and Ivan, go ahead.
Yes, can you hear me?
Yes.
Yes, okay. Breno, thank you very much for your presentation. Really interested to hear more about heat stress. So I have two questions. My first question is about Wisconsin and Texas. That you mentioned you were thinking of using a multiple trait approach. So I was thinking, how would you go over with the traits? So are you considering production traits? Are you considering the heat stress or heat tolerance component, and then using a bivariate trait, let's say, to look at the genetic correlation? Could you elaborate more on that, please?
So for that, that proposal was funded by the Holstein Association. Hopefully, we're going to start that December 11th. That's when we are hoping to get full access to the data. So we're gonna approach that in several different ways. So one, we're gonna do a more epidemiological study to see the effects of heat stress within each state, very similar from what we did with the pigs. So trying to model milk production as a function of heat load. Then when we go to the genetic evaluation, given that we are assuming that we're gonna find losses because of heat stress, then what you're going to do, we're going to do either a 4-trait analysis. That's going to be Texas not heat stress, Texas heat stress, Wisconsin not heat stress, Wisconsin heat stress, or actually, and we're going to try both, a 2-trait random regression. So one random regression for Texas and one for Wisconsin. Looking at the pedigree, we have many bulls with many daughters in both states. So that's not going to be a big problem. Of course, we won't have the same cow in both states. That's impossible. But we'll be able to build that as a function of bulls because we have many bulls with many daughters in both states. So the idea is to see if the genetics for heat stress is going to be the same across the states or not. But we'll have many testing to do for that. But roughly the idea is to start splitting, like do one within Texas and one within Wisconsin, and then putting them together in those basically random regression and multiple trait approach. Did I answer your question?
Yes, you did. Yeah, I was thinking about the random regression in a bivariate analysis.
Yeah, I mean, the problem will be if we find that's the best way to do, and then we propose to do that nationally. I don't know who will be willing to run that analysis.
Yes.
I think people from AG are going to be pretty mad at me if I ask them to run it.
Right. And so the last question I have, it's more to hear your thoughts on the idea of using or assuming a common threshold when analyzing heat stress, right? So there's a few studies, and I think from Stahl's groups, that attempted to estimate individual thresholds and apply that when estimating genetic parameters. So what are your thoughts on that? Have you worked with that in mind and trying to overcome this assumption for, a common threshold for all animals?
So that is that varies a lot too. So we see. Let me just stop sharing. I think we'll look better here. So what happened was we always usually start trying also testing a different threshold, but then it becomes computationally extremely expensive because then on top of the whole random regression, you got to find a threshold for each animal. I think in dairy cattle is going to be slightly easier than in pigs because we're going to have many daughters from each bull, so we can compare. But Usually we simplify assuming a common threshold, just because basically the convergence is much, much better. Because those analyses, that we can complicate them as much as you want, right? And the same thing with the pigs. Even the random regression with a common threshold, the companies, they don't like it very much. They rather do a two-trait approach because they don't have to worry about which hit load should they be using for those breeding values. It's okay. That's the heat stress EBV. That's the regular EBV. I'm going to come up with a weight here. I don't know how they calculate it. They come up with a weight, they put in their index, and the problem is solved. So I think that for writing a very good paper, we should definitely go after that threshold. For implementing that, the simpler the better. So our first proposal for the heat stress, the national evaluation, was rejected because we just proposed a random regression. And I said, okay, how is a dairy farmer going to use that information? So we came up with like 2 extra approaches to make it easier, so that we're talking about implementing that nationally, and people should understand how to use it. So I'm a big fan of using the random regressions, but there will be a lot of thought on how we're going to communicate those breeding values, because that's another thing. In Australia, they have it a very, very simple one, and it's working really well. I think they're doing that in their national evaluation for 5 or 6 years already, and it's working really well.
Yeah, that's awesome. Thank you for your thoughts shared.
Thank you for your question.
Thanks, Ivan. Flavio, go ahead.
Hey, Breno.
Hey.
Good to see you.
Good to see you too.
Thanks for your seminar. Breno, I have a question for you that's not related to what you did. That was very nice. It's related to method R, right? Because method R, when it was proposed in 1994, there was a kind of, everybody was excited with it for the reasons that you pointed out. They use a fraction of the data, then it's easier. But the problem is, method R is very strongly biased by selection, right? It is inherent on it. So that's why for a while nobody was using it. In my PhD thesis, I did on in this aspect of selection bias on estimation of various components, and method R was terrible in terms of. So and you are using method R for in swine. That the GC interval is very short, a lot of genetic progress there. So I guess that it's easy estimates to get, but they are going to be quite biased.
So go ahead. Sorry.
Yeah, no, I just wonder if you're aware of this, because nobody talks about method R anymore and the problems that we showed with simulation and everything. Or you think it's worthwhile to allow for bias and have like short this I mean, to reduce the computational demand. But I don't know. I would not recommend to use method R.
No, I agree with you 100%, but we didn't use that in swine.
Oh, okay.
So, because in swine we have about 200,000 records, so that went just fine. We're just using that for the dairy because then we have, if I remember it right, if we want to use the whole national data, we have about 13 million cows. And then when you go for the test day records, we go about good 30, 40 million records. So we try many different things. What actually gave us the best result, and it didn't vary that much. Now, in some traits, we had a little bit of problem too, but dividing by state was a good thing that helped to decrease those costs. and also trying to reduce the size of our files by selecting only animals with records in both states. That also helped a little bit. But what I'm hoping, we just bought a new server, and that new server should have enough memory to run, if not with all animals, with most of them. But before, you're using a server that has 120 gig only, and it was not running with more than 500,000 animals. So we had to be reducing that. Otherwise, getting those complex models, they're not even, like, each round was taking 3-4 days sometimes.
Yeah, that will be if you have a chance to in the future to compare the estimates that you are going to get with R and let's say Remo. It will be interesting. But even Tony Reverto doesn't use method R anymore.
Yeah, so there was a paper from I forgot his name, that they compared reduced, like, taking random samples and using the whole data in the US dairy, and it didn't change very much. Basically the orientation that we had was, well, can we just take a small subsample of that population and buy small 100,000 animals and run it? So I call it method R, but I'm running with at least 100,000 animals, 100,000 phenotypes in each variance component. And the results are actually following what is expected. But hopefully with the new server, that's not going to be possible. It's not going to be a problem anymore. We'll see. But that's probably one of the main challenges we have with the US dairy data. So we're cooling data collected before 2010, for example, and even that is still too big.
Yeah.
So
okay.
Yeah,
Thanks.
my student is doing a very good literature review on method R, and she was saying the same thing. Like, people are not using that. I think the most recent paper is 2014.
Yeah.
Or so.
Yeah, and if you just after 1994, when the Tony proposed this, there was a boom, lot of people using, right? And then there were like this papers like my own that show now this method is highly biased, and then people stop it, right? But I mean, I was curious to if you had tested and also if you were aware, because this is old stuff that sometimes we don't discuss anymore, right?
Yeah. So I remember I actually learned method R when I was talking about threshold models, and that was a second boom because we couldn't run without.
Yes.
So lots of people thought that method R was related to threshold models for a while.
Okay.
But yeah, but we are aware, but it's either reducing and that's actually one of the advice that I got from other people, is that do not run variance components with all animals.
Variance component what?
Do not run the variance components using the entire data set.
Oh yeah. It would be impossible to do. I agree with
Shogo did it, and it took like 2 months. So when it made the model more complicated, basically I had to reduce the sample size. So I'm doing that in several rounds, and each round has at least 100,000 animals. So the results are being as good as they can be, I guess.
But you are using the ratio, like the methodology for the R method, right?
Yes.
Yeah, but maybe the probably that ratio there, that the methodology that's going to lead to the bias. Maybe you have just to sample, get a random sample of herds, right? And then you select all animals in that herd, all the phenotypes available. So not selecting records, but randomly select records, but random selecting herds. And
we
then
did that too.
you calculate your genetic parameters, and then repeat this, and then you calculate the average of the genetic parameters.
We're going in that direction.
Not using the method R, The problem is what is behind the method R that leads to the bias, right? So it's better to do a random sample of herds, estimate the components, various components, and then another sample, and then you average over the samples.
Mhm.
I think
Yeah, that's pretty much what you're doing. Yeah, I mean, we tried many different ways. The best one was when we selected herds instead of selecting records, because when we selected records, especially on the large states, sometimes we had a couple groups with very few animals. So
yes.
yeah. So I mean, I think what I'm getting here is that what I'm calling method R is not exactly what was proposed in 1994, but I still wanted to give some merit to the idea of splitting, averaging, and rebuilding. But yeah, we actually observed that. Now that you mentioned that, when it did random records using the proportion, values went all over the place. When it did on herds, and then we exclude the some of the herds as well that didn't have enough records, the results got much better.
Yeah. When you select herds, you keep intact the number of animals within the fixed effects, right? For that herd. If you select like 20% of the records, then you, on average, you're going to reduce 20% number of observations within each fixed effect class. So you don't like to do that, right?
Yes. So yeah, that's a good. I forgot about that. So my student, she found that we had some herdier season with 1 or 2 animals only sometimes.
Yeah.
So yeah, in the second script she wrote, she's keeping contemporary groups only. So random contemporary groups, basically.
Yeah. Very good.
So perhaps we should. I'll tell her to add something to say that's not method R.
Yeah, maybe you're not doing exactly the method.
Yeah, it's not exactly what was proposed, but I want to give Tony some
recognition,
because
right?
yes, it was not my idea.
Thank you so much, Breno.
Thank you very much for the.
Good to see you.
Good to see you too.
Bye now.
Bye.
So that's all the time we have today. Thank you again, Dr. Fregomeni, for the very interesting, really great presentation. And thank you everyone that joined us today. See you all next week and have a good weekend.
Thank you.
Bye.
Bye-bye.